The focus of this lesson is going to be using factoring to solve polynomial functions. So we did factoring a lot in our last unit with quadratics in very specific circumstances. And now we're going to go through more factoring patterns and use more varieties of the factoring ideas that were in that list. So a reminder of the factoring methods that we do use. So first, we would set the problem up, and then generally we look for a greatest common factor first. It often makes something factorable that wasn't previously factorable, or makes the numbers easier, I guess, to deal with. Secondly, we look for special patterns. So this means things that we know because we've seen this pattern over and over again that factor a certain way really quickly. And so far, the only example that you know of this is our difference of squares, that we know they cancel out that middle term and make perfect squares at the end, so they have to factor in this very specific way. Beyond the special patterns, the third thing we look for is if something's fitting that specific quadratic factoring pattern. And we're actually going to see some different versions of this. The pattern for a quadratic is that you have a power of x and then half that power and then a constant. And then you can use those quadratic factoring methods that you guys do, either guess and check, your bottoms up, your diamond, and your grouping, whatever the case may be. And then fourthly, we look for grouping the polynomial. So before you can do any of this, if you are factoring, remember, is only useful to us if we have those factors set equal to 0. So first, we're going to move everything to the same side of the polynomial. Remember, you can only combine like terms. So here I would get 3x to the fourth minus 12x cubed plus 21x squared equals 0. And then I'm going to look here to pull out my greatest common factor. I'm going to kind of go through this list. So my greatest common factor is 3x squared. Every term has that value. And that leaves x squared minus 4x plus 7. So then I'm going to kind of go through my list. I've taken out the greatest common factor. I don't see anything that fits a special pattern. I do have a quadratic here, so I would try to factor that. As I look for things, there's nothing that multiplies to make 7 and adds to make 4. So though I wish this worked and went further, it doesn't. And I don't need to use grouping. So this is as factored as the polynomial gets, and now I need to solve it. So remember, to solve, you're taking each factor and saying it could be equal to 0, and that's how we're getting that product of 0. And so for this first factor, we can just divide both sides by 3 and then square root, and we get a solution of 0. For the second factor, it's more complicated. It's a quadratic and it doesn't factor any further. So now you got to think about what were your other options to solve a quadratic. So let's say I choose to use the quadratic formula. So I plug this in. And then I'm seeing in my quadratic formula, simplifying here, that this would be 16 minus 28, which would be negative 12. Now I'm going to keep going because I now have a way to express this with my complex numbers, and it didn't say real solutions, so I'm just going to continue to solve. As I continue to simplify, when I break down the square root of 12, I would normally think about it as 4 times 3. So then using I'm going to have 4 plus or minus 2I rad 3 over 2. And that simplifies to be 2 plus or minus I rad 3. So I have 3 solutions here for this, 2 that are complex and 1 that's a real number. So in order to do this, we are going to add one more special pattern to factoring. What if you see something like this second step here, but instead of perfect squares, they're perfect cubes? So you can get sums of cubes or difference of cubes. Now with squares, it only works out as a difference because you're only going to get the middle terms to cancel out if one's a positive and one's a negative, which means when they multiply together, they must be negative. For cubes, it's a little more complicated. So this is our pattern that we're saying that this is going to equal a plus b, and then here's what it would multiply. And I'll show you guys how this works. And if it's a minus between them, you get the same pattern of values, but different signs. So you don't plug in A or B as positive or negative, you just use these patterns here. The reason it has to work out like this is you'll see the A times the A squared would make the A cubed, and the B times the B squared makes the B cubed. And in this one, you get the same idea, but you get a negative B cubed. And what you need is you need all the terms in between to cancel out. So this has been constructed so that it will work out perfectly that way. When A multiplies AB, I would get A squared B, but it would be negative. And then when A multiplies B squared, I get A and then B squared. Now I'm hoping when I multiply the B through the things it hasn't multiplied yet, that I will see these cancel out, and that is what we get. When B multiplies A squared, we get that A squared B, and that cancels out that term. When the B multiplies the negative AB, we get negative AB squared, and that cancels out that term, and that's how we're left with those perfect cubes. The same thing happens in the problem below. The things cancel out, and then they leave you with just the perfect cubes. So you want to memorize this new factoring pattern. And then I'm not one for hints and tricks usually, but so one of the teachers here uses SOAP to help students remember. Generally, you have to remember these by yourself, okay? But then they say sign-wise, this is the same as what you had in the problem. This is the opposite of what you had in the problem. And this last term is always positive. And so you see the letters S-O-A-P, like soap, and that helps them remember apparently. So I'm just sharing that with you and passing it along. So we'll want to remember these things. So how we would use them is if we were solving something like number 9, you guys could go ahead and just divide both sides by 2 and then cube root and get that x is equal to negative 3. This is true, but you're only finding the weird number solutions, the real number solutions, and not the complex or other possibilities. So this found real numbers for us, but not complex. So what if we also want to find those complex solutions? Then we need to be able to see the entire way that this simplifies. So I would actually bring the 54 to the same side as the 2x cubed so that I could approach this from a factoring perspective rather than just isolating the x. So when I have these all on one side set equal to 0, I'm able to divide everything by 2 since we are solving here. And that's going to make this a little bit easier. And so now instead of solving this other way, I'm going to get all the solutions by factoring this. And so I've already taken out the greatest common factor by dividing everything by 2. And then I have to recognize this is a special pattern. These are perfect cubes, and so this would be a sum of cubes. And then to see what values the A or the B are, so to speak, you want to see what is being cubed to make your expression. So x cubed is made by cubing x. So x is going to be like our A in our pattern that we see above. And 27 is made by cubing 3, so 3 is going to be like our B in our pattern we see above. And in that pattern, the first factor is made by using each of those individually. The second factor is a quadratic, and the first term is the square of what you used here, so x squared would be x squared. The last term is the square of what you're using as the last term in that first factor, so 3 squared would be 9. And the middle term are these two things multiplied together, so 3 times x is 3x. And then you have to remember the appropriate signs to use. So we were factoring a sum, so we use the same there, the opposite here, and the positive here to make sure it would work out as that perfect cube. Now you can try and factor this quadratic further, but it doesn't factor. So we're kind of like we were in that first example. We're setting each of these factors equal to 0. And so here I'm getting -3. Here it's not factorable, so I'll use that quadratic formula. So when I do the quadratic formula, I have 9 minus 36, which is -27 inside of that radical. And I'm going to think of 27 as 9 times 3, which would give me 3 plus or minus 3i rad 3 over 2. And that cannot be simplified. So I have 3 solutions here, 1 real number and 2 complex numbers. And since it didn't leave me with directions for just the real numbers, I'm going to list all of those as my solutions. Okay. So our real goal here is using that one factoring problem. I do want to add one thing in here because of your homework. So I just want to point out, because I don't know if all of you are familiar with what I mentioned before, that quadratic factoring pattern that you guys are used to. So like, let's say we had x squared plus 3x plus 2, and then you guys are pretty decent at factoring this as x plus 2 times x plus 1, no matter which method you use. Now let's say that I changed this to the same numbers but different powers, as long as those powers still follow the quadratic pattern. So this is the first power, this is half that power, and this is constant. It still is going to factor just like a quadratic would factor. You just need higher powers of x. So you're still going to use the same numbers, but instead of these being x's at the beginning, they're going to be x squared, so that when they multiply together, they don't make x squared, they make x to the 4th. And when they add together in the middle, they make a term with x squared, not x. And so the same thing would be if I made this x to the 10th plus 3x to the 5th plus 2, that this would be x to the 5th plus 2, x to the 5th plus 1. Same numbers, but making those different powers of x. So I just wanted to reiterate that, because as we look at these factoring steps that we gave you guys, there's not just a quadratic here, it's anything that fits that quadratic pattern. You can still factor even if it's higher powers. So I just wanted to make sure you guys were aware of that.